It's a pleasure to introduce the last speaker of this meeting, Urs Frauenfelder from Augsburg, and he will tell us about gateways to the moon and local Floer homology.
Thank you very much. And because I'm the last speaker, I think we should first thank the organizers for their wonderful talk. Now? Okay, good. Okay, so title of my talk is Gateways to the Moon. And local Floer homology. And this is a joint work, joint with Edward Belbruno and Otto van Kurt. And let me first start with the problem of a falling stone. So what is this problem? So problem of a falling stone. So we have the following situation. We have here the Earth and here the Moon. So the Earth and the Moon they are in one plane, ecliptic, and they move. They move in this ecliptic. So Earth moves and the Moon moves. And we have a stone, and the stone is it's 3D, so it's above the Moon, and it starts with the same velocity. So here we have the stone. So you should imagine this in 3D. So here is the Earth, like here is the Moon, and the chalk is the stone. So the chalk is here, and the Moon moves, and the chalk moves first in the same velocity. And we want to know if the chalk hits the Moon. But you have so you imagine these two move, and they will attract the chalk, but then they are at a different place. So what we see, the chalk will somehow fall down. But the question is, does the chalk hit the Moon? So question is, does the stone hit the Moon? And so what is clear, it somehow falls down. So here the Earth moves, Moon moves, and the stone somehow falls down to the ecliptic. But how it falls is difficult to tell. So we can, instead of having a moving Earth and a moving Moon, we go to rotating coordinates, so the Earth and the Moon are at rest. So in rotating coordinates, we have, call it E and M, E for Earth and M for Moon, at rest. So we have here the Earth fixed and the Moon also fixed. Here is the plane. And then in these rotating coordinates, the stone above the Moon also starts with 0 velocity. Here is the stone. So initially at rest. The Earth. Then, but if we are in rotating coordinates, so what happens to the stone? So the stone will experience different forces. So there is of course gravitational force of the moon. There is also gravitational force of the Earth, but now we are in rotating coordinates, so the poor stone will also feel some centrifugal force. And there will be actually a fourth force, the Coriolis force. And the Coriolis force, at the beginning we don't have yet, but if it starts moving, the Coriolis force is velocity dependent. So we have then some force for Coriolis force, velocity dependent. So also in rotating coordinates, it's not so clear what's going on because there are these four forces. So let's write down the Hamiltonian. So we have a parameter mu. Mu lies between 0 and 1, and mu corresponds to the mass of the moon. So mu is the mass of the moon, and the total mass is 1. So our kilogram is the mass of the Earth and the moon. And the position of the moon and the Earth, so the moon is at 1 minus mu 0, 0, and the Earth is at minus mu 0, 0. And then we have the Hamiltonian. H mu from the cotangent bundle of R3. So we remove collisions with the Earth and the Moon to R. So QP, Q position, P momentum, it goes to kinetic energy. Then we have the potential energy, so the mass of the Moon divided by the distance to the Moon minus the mass of the Earth divided by the distance to the Earth. And then, because we are in these rotating coordinates here, we have an additional term, which is angular momentum, and this takes account of the rotation, P1 Q2 minus P2 Q1. This is angular momentum. That generates the rotation. And if I complete the squares, so I can also write this Hamiltonian as 1/2 P1 plus Q2 square plus P2 minus Q1 square plus P3 square minus mu divided by mass of the Moon divided by distance to the Moon, mass of the Earth divided by distance to the Earth. And then, because I have this completed the square, I have minus 1/2 Q square. And then in this description, we can see these four forces. So we have, so here we have obviously gravitational force of the Moon, we have gravitational force of the Earth. So this last term, this gives rise to centrifugal force. And then here we have a twist in the kinetic energy. So this twist here, this gives rise to the Coriolis force. That's how one can read this Hamiltonian. Now, we want to go to a limit case. And this limit case is kind of miracle. Namely, what we want to consider is the Earth becomes heavier and heavier and heavier. And the Moon is, of course, still much heavier than the stone, infinitely heavier than the stone, but also infinitely lighter than the Earth. So we cannot compare any of the masses anymore. Yeah. Yeah, so Moon and Earth, they satisfy a Kepler problem. So this is a two-body problem, and in rotating coordinates, then this follows from the Kepler solution. So yeah, right, we consider kind of the circular case. We assume that the center of mass is at the origin here, and they move in the original coordinates. They move around the center of mass in circles. It's a so-called circular restricted three-body problem. So I like to discuss Hill's lunar problem. The Q square here. I completed the squares.
Yeah, but there is a Q3 squares that appear in the second line.
Sorry, there's sorry, you're right. So this is Q1 square plus Q2 square. Right. Yes, you're right. So we have here E, the Earth is much heavier than the Moon. So we let mu go to 0, and we assume that S is close. The stone is close to the Moon. So we have this picture. We have a heavy Earth here. We have a rather tiny Moon, and we have very tiny stone. And then what we do first we put our origin of coordinates here to the Moon, and also we do center coordinates at M, and then we blow up the coordinates here. So we look here at some tiny neighborhood of the Moon, and we consider the transformation QP, so we blow them up with mu over 3, Q mu over 3 P. So we also blow up coordinates. So this is not symplectic. So this is just conformally symplectic, conformally with the factor mu to the 2/3. And then we rescale the Hamiltonian. So what is actually whole is the Hamiltonian vector field. The Hamiltonian vector field we don't want to change. So if you change the symplectic form by mu 2 to the 3, we also change the Hamiltonian. So we rescale the Hamiltonian 1 over mu to the 2/3 and h mu, and this is now a bit dangerous because we want to let mu go to 0. So we add here 3 over 2. So this 3 over 2, of course, this does not really influence the Hamiltonian vector field, but it will influence the limit. So this is our new energy. So if this new energy has is different from the old one. So if you want to go back, the new energy times mu to the 2/3 minus 3 over 2. This would correspond to the old one. But what under this transformation does not change is the Hamiltonian vector field. So note the XH, the Hamiltonian vector field, is a scaling variant. So the Hamiltonian vector field is. So we scale the symplectic form, we scale H, so the Hamiltonian vector field does not change. Now the first miracle which happens when we do this, so this is that we can take the limit. The limit mu goes to 0. This will give us a limit Hamiltonian. Also miracle 1, mu to 0, the limit Hamiltonian exists. And what is the limit Hamiltonian? So let's write down the limit. So H, this is now on cotangent bundle. Oh, we have now the moon. The moon is now at the origin, and the Earth escaped to infinity. So we have just one singularity left, 0 to R. And we have QP goes to 1/2 P1 plus Q2 square plus P2 minus Q1 square plus P3 square. And then what is left from the last terms, first write just down, so is minus 1 over Q, then we have minus 3 over 2 Q1 square plus 1 over 2 Q3 square. So what, let's do some physical interpretation what we see here and try to understand if we can what's going on if you go to this limit. So you can do is mathematically you do some Taylor approximation, but then you will not see what really happens. So what we still have here is the Coriolis force. So we have here the Coriolis force. And this term is also pretty clear. This is now just the gravitational force of the moon. This is gravitational force of the moon. So these last two terms, these are more strange. And so what happened here? So you have to imagine there was a big fight between two forces. So there are the two forces which are fighting heavily against each other. This is once the gravitational force of the now extremely heavy Earth, and it fights against the centrifugal force. No, yeah, everything. I pull back everything down. Yeah, I pull back everything down.
So what happens with this symplectic form when you take the limit? So we're taking the limit of the Hamiltonian, right?
Yeah, but I pull it back to the standard symplectic form. Also this H is again taken with respect to the standard symplectic form. So let's from physical interpretation. We have here the extremely heavy Earth. Here the little moon. And then the stone. And we have here a very heavy gravitational force but now our center of mass is now in the very heavy Earth, basically. So we have if you think we have an enormous merry-go-round now. So we have our merry-go-round is now billions of kilometers. So we have also a huge centrifugal force. And these two basically cancel. So what is left over from this big fight are these two last terms. So we have the left over is minus 3 over 2 q1 square plus 1 over 2 q3 square. So what's this? This you can think of kind of tidal force. So it will so here at the moon you will feel some force symmetric going out on both sides. That's kind of a tidal force. So this is repulsing, and this here, this is attracting, and this is kind of clear that you have an additional attracting force, since now you, if you just look in the Q3 component, we have of course the gravitational force of the moon, but the Earth is still in the plane. So this will make your force back to the ecliptic stronger. So that's why we have here a plus sign. So this is the kind of leftover of gravitational force. Of E. Now let's look at the symmetries we have in this problem, and then we will see an additional miracle happen, which is quite not far from obvious when we see this, how this appeared. So we have symmetries. What symmetries do we have? So for H nu, for the old we have first a symplectic involution from T star R3 to T star R3. This is Q1, Q2, Q3, P1, P2, P3 goes to Q1, Q2 minus Q3, P1, P2 minus P3. This is a symplectic involution. And what is the fixed point set of this involution? The fixed point set is precisely the planar problem. So the planar problem here arises as some subproblem of the spatial one, and you can interpret it as the fixed point set of this symplectic involution. So fixed sigma, this is T star R2, and this is the planar problem. Now we have another involution, this time not symplectic, but antisymplectic. So we have row 1, T star R3 to T star R3, Q1, Q2, Q3, P1, P2, P3. This goes to Q1 minus Q2. So Q3, but then we have we have these terms, and we also, so we take here, we take P1 to minus P1, P2 is fixed, and minus P3, so that these two terms, they become both a minus. So this is an antisymplectic involution. Which commutes with the previous symplectic one. So as a note, we have rho 1 sigma equals sigma rho 1. But now, and these two involutions we have already in the restricted three-body problem. But now, in this, for this Hamiltonian, we have an additional involution, which does not hold in the restricted three-body problem. Namely, we have rho 2 miracle 2, we have H, not H mu, but just a limit Hamiltonian. H is invariant as well by, so it's rho 2, T star R2, R3 to T star R3, Q1, Q2, Q3, P1, P2, P3 goes to minus Q1, Q2, Q3, P1 minus P2, P minus P3. So we have some additional antisymplectic involution. So the old symplectic involution, this corresponds to reflection at the Q1 axis, at the x-axis, and this is because on the x-axis there were the Earth and the Moon were on this axis, so you have reflection invariance with respect to this axis. But the third involution, this we don't have in the restricted three-body problem, because this is reflection. This corresponds to reflection at the y-axis, and in the old problem, this was of course not invariant under this reflection. So we have different masses. But now, in the limit, when the Earth goes in this direction, it looks we could have as well let the Earth go in this direction. It doesn't matter. So in the limit, we get this additional symmetry, which is kind of a miracle that we have this. So now and this now we have two antisymplectic involution, and they again commute. So we have rho 1, rho 2 equals rho 2, rho 1. This is again a symplectic involution. 2 times minus is plus from T star R3. Q1, Q2, Q3, P1, P2, P3 goes to minus Q1, minus Q2, Q3, minus P1, minus P2, P3. This is a symplectic involution. And now what you see here, for the symplectic involution, the z-axis is invariant. So the z-axis is invariant. And what does this mean for our stone? Namely, in this limit problem, the stone just falls down. So because it's invariant set. So if we start here on the z-axis with 0 velocity, then it has to stay in this fixed point set, and that means in this limit case, if I have a stone, we still have here we have the moon, here we have the Earth is now very, very far away. So here is the Earth, but now in this limit case, if I have a stone here, it just falls down. So we have S here, and here is the moon, and then we S falls down straight to M. Now, in this, so this is actually, yeah, the stone is now destroyed. So it collides with the moon. But in this two-body collision, one can always regularize. And this topic of regularization is we will discuss actually more in the coming week in our lectures on the sim. But if you regularize it, what happens if you regularize it? The stone falls down to the moon, and then it just bounces back. So it does something like this. So regularize collision so that in S bounces back. Sorry? Polyfolds? Yeah. No. That's why there are no polyfolds. No, this is
No, I'm making a really bad joke.
no, it's good joke. But the mathematics behind this regularization I will discuss next week. So, but you can imagine basically what happens. It falls down and bounces back, and then it does this forever. So we have this. So here we have the moon, we have the stone, it falls down, bounces back, then falls down again, and so on. So what's that? That's something we all like, because this is a periodic orbit. So we found a periodic orbit. So actually we can give this stupid thing, this stupid stone, which always does like this. We can give this kind of 4 interpretations, and 4 interpretations which make sense in the restricted 3-body problem. That means I cannot in the restricted 3-body problem, I don't have rho 2 anymore. But I still have rho 1 and sigma. So I can give this orbit 4 interpretations in terms of sigma and rho 2. Namely, how can we think of this orbit? So we have 4 interpretations, which all are making sense in a restricted 3-body problem. We can think of this orbit as a consecutive collision orbit. yeah. That's we have here a collision, roll back, again a collision, and yeah, I will explain more coming week. But a consecutive collision orbit, this has some kind of open string interpretation. So the collisions you can think of kind of Legendrian, and this is a chord from a Legendrian back to a Legendrian. So this is one interpretation as a consecutive collision orbit. Then we can interpret it as a symmetric consecutive collision orbit because it's symmetric with respect to row 2, row 1. As a symmetric with respect to row 1 consecutive collision orbits. Yeah, right. The symmetry extends to regularization. Yeah, yeah.
So you get a symmetric
Right. So that's a fourth interpretation. So interpretation number 3 is it's a periodic orbit. First, we don't care about the symmetry, and then, as you say, the fourth interpretation is symmetric. And to all of these 4 interpretations, there is a Floer theory. So you can, yeah. And you also have kind of equivariant Floer theories. So a lot of things we learned this week, yeah, you kind like this stupid thing here, which just bounces back and forth. So we have kind of 4 Floer homologies. So now let's bring the Earth back. Huh? So here is the Earth, we moved away, now we bring it back. So we make mu positive again, so that we can again compare. And we think of this mu now as a parameter of the problem. So make mu positive again. So in the interpretation as a periodic orbit, so for mu equals 0, we have this orbit going back and forth. But now, if mu is positive, we have kind of this. This becomes a periodic orbit. It's a kind of a polar orbit. So here, this is in 3D. So here is in 3D. Here is our moon, and our orbit will do something like this. Yeah, it's because of the symmetries. It's satisfied again some.
Because if you had that additional symmetry only in the limit, right?
Okay, so it might not completely be polar. So it's maybe a bit, so something like this, but close. But if mu is not too big, then it's close to this. So it does something like this. And then in the interpretation of the consecutive collision orbit, so this we actually didn't carry out so much, but you can also do this interpretation. So what you would get here is, so again we have for mu equals 0, we have this, mu equals 0, and then we would have, then it would not be a periodic orbit, but still consecutive collision orbit. But then then we go somehow, we think of this as a Legendrian, so it goes from this Legendrian back to the Legendrian, but it might come back with a different speeds. So it's usually we cannot extend it in a periodic way. Well, this is for mu bigger 0. Yeah, and this here, this is kind of a possible gateway to the moon. So that's this is kind of. Did you know that now on the moon, people discovered water? So I learned this recently from when Edward Bruno was in Augsburg. He invented Jim Green, the chief scientist from NASA, and he told us about NASA's plan. And what he explained to us is that now NASA found water at south and north pole of the moon, and this really changes the game, as he told us. Because now there's according to him, the plan is in 5 years to go to the south pole of the moon, send a female astronaut, and look about the water at the south pole of the moon. And then if you have then for communication, such a tool might be useful. But we have to know that there are engineers also have these kind of tools, but they do it from a different point of view. And this makes it quite interesting, especially if one has all these Floer homologies behind this. So what is now the engineers' approaches to gateways to the moon? Other approaches. Gateway. So this goes back to a paper by Howell and Breakwell, which is called Almost Rectilinear Halo orbits from 1982. And there is also a more recent paper by Bucci, Lavagna, and Yin. And so what they do, these halo orbits, this is the following. So we have here we have the Earth, we have here the Moon, and then we have Lagrange points, here L2, and around this L2 we have in 3D such a halo orbit. So this is not yet around the Moon, but this halo orbit also gives you a family. And you can follow this family, and this family has the property, as this is discovered, that it also moves to the Moon. So the family moves to the Moon. So we have some family. So that's the different way how you can get this these polar orbits. And now, of course, the question is, are these the same? Or so what can one say in this region about families of orbits? What kind of theoretical tools we have also from symplectic topology? So question. are these families the same? And here I would like to mention some recent progress. Symplectic topology. Topology of this restricted three-body problem. So that's by Zhou and Kim. They proved that the spatial restricted three-body problem below and slightly above the first critical value admits a contact structure. So before that, we showed this result also with Albers, Patenheim, and Van Coort. We showed this for the planar case, but now they can also do it in the spatial case, which is relevant here in this topic. So the spatial restricted three-body problem below and slightly the first critical value is contact. And I would like to the end of this talk tell something what this contact geometry tells us about families. And namely this contact topology provides families for escaping. So that's so we have the so-called omega limit set of a family. And so suppose that M omega, some symplectic manifold, and H mu to R for some parameter mu is a smooth family of Hamiltonians. And so let's assume that 0 is a regular value of H mu for all mu 0, 1, so that we have energy hypersurface with sigma mu plus H mu inverse 0. So these are closed hypersurfaces. And suppose we have a family of periodic orbits. So we have so the family exists up to some parameter mu 0. So we have some mu 0 bigger 0. And we have some V. Now we have a one parameter family of orbits. So we have two parameters, S1 for the orbit and then the family parameter. and here we have open. We don't have it at mu0 yet. We have it just before to m. This is smooth. And we have also some periods, tau, 0, mu0 to 0 infinity, smooth, such that dtv t of mu, so we fix mu, we look at the t derivative, equals this period x h mu v t mu for t in S1 and 0 less than or equal mu less than mu0. And they are on this, they lie on this hypersurface, so we have h mu v t mu equals 0. So if I write subscript u, this is a periodic orbit on sigma mu of period tau mu for all mu in 0 mu 0. And for up to mu 0, we can let's assume that they are non-degenerate. So we start with our collision, and then first we have by implicit function theorem we can continue a bit. So they are first non-degenerate. So assume phi mu is non-degenerate. For all mu in 0, mu 0. And then we define omega limit set omega v. These are all limits we can obtain when mu goes to mu 0. These are w from S1 to sigma mu 0. Then there exists mu converging to mu 0, mu to infinity, such that the w is obtained as the limit of the v mu to infinity. But maybe we can choose different sequence. Different sequence will give different limit. So it's not clear that this is just one. So that this is what we call like a limit set. And now what a priori could be empty. And this, if it's what could happen here is that the period explodes. But this is precisely what contact structure helps us. The contact structure prevents this period from exploding. And so this period cannot explode, and so that you can use this fact to show that this is not empty, and you can even do more, because if this period doesn't explode, you can also look at playing with subsequences of subsequences. So it can have some fun or with and to have some structural result about this omega limit set. So, why the period doesn't explode? Yeah. So maybe right. So maybe let me make the statement and then explain something about the period does not explode. So the theorem of with Bruno and van Kurt is if the sigma mu is contact for mu in 0 mu up to mu 0, then this omega v, this is non-empty compact connected, and using this one can then associate to this omega v a local Floer homology and then can associate to omega v local Floer homology. So, okay, so the question, why does it not explode? So let me just briefly indicate. So that's we have variational approach to these periodic orbits, and for example, we can use this Lagrange multiplier function, which was also used by Rabinowitz. So we have the AH mu. So we have here we have the free loop space, and we have a loop and a tau, and we map this to the integral v star lambda minus tau integral h mu v t dt. And the critical points of this function are precisely the periodic orbits. So we have a crit AH mu correspond to periodic orbits. And tau is then precisely the period. And then what the contact condition gives us, the contact condition, so we can arrange this in such a way that this H mu is precisely the Reed vector field, and then the critical value, so if V tau is a periodic orbit, then we have AH mu V tau is precisely tau. And then now we can look at the how the so we differentiate with respect to mu, ED mu, AH mu, V mu tau mu. These are critical points. So the dA at this critical point is 0. So we get here this equals minus let's absolute value. So we have here the tau mu, and then we have this is some derivative with respect to mu, which is something bounded. So this is something integral h mu v mu t dt. So this is less than or equal to a constant, and this here is by the contact condition. This is the action value. So you see that the derivative you can estimate in terms of the action value times a constant, and then you see it can grow at most exponentially, and it cannot explode. So this is if the period explodes, it's called a blue sky catastrophe. And using this contact condition, you exclude these blue sky catastrophes, and that gives you the non-trivial omega limit side. Thank you for your attention. I stop here.